Hello, my name is Simon Harris. I'm a second year math major here at UAB. I'm part of the Science and Technologies Honors Program, as well as I am part of the Fast Track program for math. And today we're going to be looking at the El Niño, which is a naturally occurring phenomenon that can be modeled using differential equations. And then we can look at those differential equations and modify them and see how the climate can be affected and what we can learn about the climate from those differential equations.
They're coming for you, Barbara.
Stop it! You're acting like a child.
Science Uncensored.
Ladies and gentlemen, boys and girls, welcome to the SciTech podcast, where we leave no stone unturned. That is Science Uncensored. Science Uncensored roll call.
Charlie.
Simon.
Kush.
And I am Alan Waring. Thank you for joining us, esteemed guest. We're talking about El Nino today. Simon, talk to us about El Nino.
All right, so El Nino is a naturally occurring climate event. It's characterized by unusually warm ocean temperatures, and it causes heavy rainfall and flooding in places like the southern United States, the western United States, and then droughts in places like Australia and Indonesia. And it also leads to the disturbance of many marine habitats and fisheries. And this event can be modeled using differential equations. And for anyone who's interested, we will have a link below that leads to the derivation of the differential equations, and also we'll have an email address that you can email any questions you have, and I'll be happy to answer them for you.
Cool. So I'm gonna cut you off. I have two questions.
All right, shoot.
Why is El Nino important? And how did you learn about El Nino? Because after talking about it, beforehand, I had no idea what it was prior to us researching it. So
So I'll start with your first question, or your second question. Sorry. I learned about this climate effect in my differential equations class here at UAB. We had to do an assignment on it, and the assignment is kind of where we get the importance of this model. So within this assignment, we derived the differential equations, and then we plotted the solutions to those differential equations. And so we can see from the graph that we can't really predict the El Nino, because anytime the graph goes into the positive quadrant, that's the occurrence of an El Nino. And so there are times where we can see that there are occurrences of El Nino that are about a year or two apart, but then there are some spans that are more of like 10 to 20 years apart. And so this model really isn't for prediction. The model is more for seeing how fragile our climate is. So by doing this, we look at one of the constants out of many in this equation that are related with the natural effects. And so one of the graphs where we change the constant, we can see this drastic change, and we'll have these graphs up on the screen for those in the video podcast. And so this graph here shows that by changing one of these constants, that the El Nino won't occur anymore. And so what we tried to do in this assignment was find a value for this constant that essentially turned off the El Nino. And so I have two graphs here. The value of the constant here is changed by one decimal place, a tenth. We took a tenth off, and when we did that, we have this graph that it doesn't occur anymore after this point. And then we changed the constant one more time. We added that tenth, and we can see that from the graph that the El Nino occurs again. And so we can see that by changing this one constant out of many in this model, that our climate is a fragile thing, that can be changed by, like, the smallest change you have large repercussions. And so we need to be careful and protect our climate on Earth that we have.
Is that constant in arbitrary units? Because I see that El Niños usually occur between 3 and 7 years, right? And they usually last about a year itself. The El Niño itself is considered a change in temperature and currents in the ocean, or what exactly is? I don't know how to ask that.
What exactly is the definition of the event that is called El Niño?
It's like I was explaining at the beginning. It's the unusually warm ocean temperatures that change the climate, and so those warm ocean temperatures are going to have like effects in the atmosphere, which is going to cause either the lack of rain or the increase of rain in places like the United States, and so that's what we're looking at.
Cool. So how can we apply maybe learning about El Niño as a model? Because I understand that it's hard to compute all of the data by hand. We have to use computers to compute a lot of the data. And, with all of the information coming out about the planets and Mars having water and maybe some other planets or moons and stuff that could maybe have water, thinking about life-sustaining atmospheres, could we use the El Niño model in other places in the solar system?
I think we could. We would definitely have to, I think maybe change it slightly with however that ecosystem is set up. But I definitely think we could take this and apply it to other planets and other places.
Cool.
So you said the basis of how the El Niño model is formed is originated at the changes in oceanic temperatures, which then changes a whole bunch of other stuff that you can measure too. But the basis of it is oceanic temperatures and currents. If another planet, like we're just talking about, doesn't have oceans or doesn't even have water, would El Niño even be capable of assessing any possible life on that planet?
No, because the El Niño, like we were saying, is based off these ocean temperatures and these ocean waters, and so if there's no water, then there's no El Niño.
So if we wanted to use climate to classify a possible habituation planet, then we would have to change El Niño or use a completely different thing.
Correct, yes.
So is El Nino, this differential equation, is it a model for El Nino or is it something else? And if so, how is that pertinent to us and why is it important?
It is a model. It's not a prediction model.
Right.
It's just.
So a model is just a variable, basically.
Yeah, it's just like an extrapolation of a possibility of an El Nino timeline.
Okay, so the possibilities of it based on, you said temperatures and
Yes, temperatures and ocean current speeds.
So based on that is how we model how severe the El Nino is going to be?
Not even model how severe it is, just model a timeline of possible El Nino occurrences.
Okay.
We can't say, oh, looking at this model 5 years from now there's going to be an El Nino.
So, but based on the idea that you already have, can you say, okay, temperatures are, this at this point in time, there are these, and this is an ocean current activity, right? At this point in time, can you use that to find a point on this differential equation to find a certain value that would tell you how severe El Nino is going to be for that year? Or is it just based on too many variables where you couldn't really focus on that?
I think that would be based on too many variables because, again, this is a naturally occurring event, and so we can tie mathematics to naturally occurring events, but something like this that isn't so set in stone, like comparing it to physics, which is very set in stone, we can tie mathematical things to physics exactly. This isn't set in stone like something in physics would be, and so it's harder to tie the mathematics directly to them to predict it.
So cutting back into the physics of it and the math behind all of this, because I think this is really interesting. Looking at some of the data that you worked with, you worked with something called Newton's law of cooling, and that had to deal with the temperature in the western end of the box. When you make the El Nino, you box in that area you're looking at. What is the Newton's law of cooling?
It's essentially a dampening effect.
Okay.
And so, very briefly, a dampening effect is, for instance, in a spring system, a dampening effect is like the air resistance that resists the spring, and so you have to what's the word? You have to account for it in the model, like if you're modeling the spring system, and so that's essentially what Newton's law of cooling is here. It's that dampening of effect that we have to account for within the model.
Awesome, cool. Well, I think we've asked a lot of questions of you today. For the viewers at home and the listeners of the podcast, if you have any questions, please email us at uabsthmedia@gmail.com or comment in the video below, and we'll be happy to answer all of your questions. Simon is clearly the expert on this, so you'll probably get a nice reply back from him.
Again, ladies and gentlemen, this has been Science Uncensored, where we leave no stone unturned. See you next time.